get started. So today we'll be talking about some more ensemble methods. So last lecture we talked about bagging, and today we'll be primarily talking about a method called boosting. So, and I guess I'll also overview ensemble methods from a broader perspective as well, but the bulk of the lecture today will be about boosting. So ensemble methods are motivated by, well, they're motivated by many things. One way to motivate them is to think back to generalization error. So recall that test error, or the error on the true distribution, is something that is unknown to us. This is to a large extent a theoretical concept. So what is the error on this true distribution of data points? What we have access to in supervised learning is a sample. That's our training data. Each data point is sampled independently from this test distribution, and then we train a predictor using this training data. And so because we assume that this sampling process is random, in this thought experiment, the data set, capital S, is a random variable. And in the thought experiment, we could pretend that we can maybe repeat this process and ask about what would happen in expectation, what would be the variance. And so H sub S, if you recall from the definition, is the classifier or the regressor that from a function class that is the output of training on this data set S, which is the random variable. So this is a random function whose randomness depends on the randomness of sampling the training data. And so from this, we can talk about expected test error of a learning approach as a function of the randomness of the training data. So this is the expected test error of this guy. And overfitting happens when the test error is much, much higher than the training error. That's a high-level conceptual description for when overfitting happens. And so when we think about this, just as a cartoon, we saw this in the previous lecture, is we have our true distribution from which we sample a training set. We train a classifier on this training set, but we actually care about test error, which is the expected error on this distribution and not on this finite sample of this distribution. Okay, so the expected test error as a function of the randomness of our training set can be written like this. So nothing has changed from the previous definition. I just wrapped everything inside another expectation, which is the expectation of the randomness of the training set. And now S is a random variable, and so the predictor we get out from this learning algorithm is also a random function. And the randomness depends on the randomness of the training set. So from this definition, we can now talk about the bias variance decomposition. And again, I'm only showing it for squared error because it's mathematically the simplest. If you care about what the bias variance decomposition looks like in precise mathematical formulae for other loss functions, you can Google it, I guess. But the precise mathematical formulations are not so important for this class. The most important thing you can get out of this class is to understand that this decomposition exists, and we'll just concretely talk about it in terms of squared loss because it's mathematically simplest. And so for squared loss, this formula, so now this can be decomposed by just using some algebraic manipulations into these two, and exploiting linearity of expectation, so we could swap around these expected values because they're linear operators. And so we get this term, and this term is the variance term, and this term is the bias term. Capital H is the expected prediction on input x. So it's formally defined like this. So capital H of x is the expected value over the randomness of the training data of any predictor you trained on the training data, and you measure its output on input x, and you average over the randomness of the training set. So, and the bias term is just the squared error between the true label y and the average prediction. So one thing to note from this decomposition is that the variance term is completely independent of the ground truth label. It does not depend on y at all. It's simply looking at the variability of a prediction of a model or a predictor that you train versus the average predictor. And we saw this at play when we looked at a very simple example of one-dimensional regression, where x is just a single one-dimensional value and y is a regression problem, so it's one-dimensional real value. And so the test data are the red dots, and we try to fit linear, quadratic, and cubic function classes to random subsets of 7 data points. And we repeated this process 1,000 times to get these plots where the black lines are the average predictor, and the green lines correspond to the variance of the predictions of any individual model we train relative to the average predictor. And we can actually measure the bias variance trade-off for each individual data point, and that's shown in the bottom row. And the total test error is the sum of the green line and the black line summed across every test data point. Some models experience high test error due to high bias. The model class is too simple. So even if we have infinite data, the linear model class will still not perform very well. Some models experience high test error due to high variance. Even though in expectation, the cubic function class seems like a very good fit. If we only had, if our training set is only size 7, the variability of the predictions greatly overwhelm what happens, what seems to be good performance in expectations. So the cubic function class is low bias, but high variance in the case where the training set is only size 7. So from that motivation, we can now talk about ensemble methods. Ensemble methods are meta frameworks or meta algorithms that figure out ways of combining multiple learning algorithms or models and then combining their predictions to form a joint model, also known as an ensemble. In the previous lecture, we talked about bagging and random forests. And today we'll talk about boosting and a little bit of a method called ensemble selection. The reason why it's called a meta learning approach is that it does not innovate on the base learning algorithm. So for example, in bagging, it's literally just like a 5-line wrapper, for-loop wrapper around your base learning approach, where you create new training sets via bootstrapping. You train a model, and then you average their predictions, the outputs of these models. So it's literally just like a 5-line wrapper around whatever learning algorithm you're using. So why do ensemble methods work at all? There are many ways to try to answer this question, and I'm only going to talk about one way in this class, and that is through the perspective of the bias variance decomposition. So bagging, as we saw in the previous lecture, reduces the variance of low bias models. Right, our base model or predictor that we're training are these really high capacity decision trees, which have very high variance and very low bias. And so what bagging tries to do is it says, well, we had this thought experiment where if we could magically collect more training data in the same procedure, and we looked at the bias variance trade-off and we just averaged the predictions, well, the variance would go down and the bias would stay the same. And so bagging was a way to try to simulate that as much as possible through the process called bootstrapping. Today we'll talk about boosting. And boosting reduces the bias of low variance models. So low variance models tend to be ones that have high bias. So a shallow decision tree being the one that we'll focus on today. And what that means is that you tend to get the same model or predictor over and over and over again with random samples of the training data from the test distribution. But of course, they can't fit the data well because they have very low model capacity. So what boosting does is it trains a sequence of these simple models so that their sum is designed to be modeling a more complex decision surface than, let's say, a simple decision tree, which is the simplest of which is just one single axis line boundary. And so that's boosting, right? The idea of boosting is that you're boosting a weak model to be more accurate. That's where the term comes from. Yes, question?
So with bagging, you're essentially taking many different models from the same class and then averaging their predictions. But how do I know that that class of models forms some sort of like convex set so that the average is still within that class of models? The average of their predictions.
Oh. Okay, so the question is is there a decision tree, for example, that has the same exact behavior as the average of a bunch of decision trees? And in general, the answer is no. In general, the answer is that this averaging, the space of decision trees is not continuous, and therefore this averaging will not lead to a decision tree in general. You could replace the decision tree with whatever complicated model you want. In general, the answer is no. It's really about the expected value of this process. Yeah. So I only care about the input-output relationships of these functions, not whether or not the average function lives in the space. Yeah, in general, that. Okay, so in this lecture, or for most of this lecture, we're going to talk about shallow decision trees. A shallow decision tree is a decision tree with only a few nodes. And the consequence of that is that they have very high bias and very low variance. So different training sets lead to very similar trees, and the error is high, often barely better than a simple baseline like random guessing. The extreme case is called a decision stump. A decision stump is a tree with exactly one split. So like this guy right here. The decision stump. It is exactly a single axis aligned split of the data. So it's even simpler than a general linear model. Because a general linear model can split across multiple dimensions simultaneously, like a general hyperplane. This has to be an axis aligned hyperplane. It only splits along a single dimension of the data. Okay, so they tend to learn more or less the same model. Therefore, this predictor, as a function, which is a random function, whose randomness depends on the randomness of the training set collection process, has low variance, right? You tend to learn the same function over and over again, even as you collect more training, redo the process of collecting training data. So in terms of the bias variance trade-off, the variability of any individual H sub S is going to be very low relative to the average H. So here's just a simple pictorial example where we learn a decision stump in a 2D space. We collect a different data set from the distribution, and you sort of learn the same, basically a very similar model, and each individual one has looks very close to the average prediction. So in the literature, people often refer to this as what's called weak learning. So this is best explained in terms of classification. The terminology is more easier to explain in terms of classification. So let the error rate be the 0-1 loss, and assume for simplicity that the classes are balanced. So random guessing gives you an error rate of 50%. A weak classifier is one whose error rate is slightly better than 50%. And a weak learner is a learning approach that can learn a weak classifier. So, shallow decision trees are weak classifiers. They can get you. They'll be able to get you a classifier whose accuracy, you can expect it to be slightly better than random guessing. It's a single split along a single feature. You can't do much with that, but it's probably a little bit better than random guessing. And the learning algorithm for learning a shallow decision tree, which is just a simple one-step recursion of the top-down learning algorithm, is a weak learner. And these weak learners result in low variance, high bias predictors. Okay, now we're going to talk about how to boost a weak model or a weak predictor. So if we think about this bias variance decomposition, right? So the problem with weak learners and weak models is that this bias is really high. This variance term is already very small. If I had the slot experiment or resample the data again and train a different model, the variability of each individual H sub S to the average H is already super small. So the problem is that this guy is really high, whereas in bagging it was the opposite. In bagging, we had really high capacity decision trees, and so the average predictor is going to have very low error relative to the ground truth. Why? It's just as each individual predictor has super high variability compared to the average. And that's why we did that whole bootstrapping and averaging, because it reduced the variance. So now, because we have low variance, high bias models, each H sub s is low variance but high bias, we need to figure out a way to reduce the right term, the bias term, through some sort of ensemble method. And that's what boosting does. So here's a first try for regression. And we're going to do one-dimensional regression. I'm going to learn we're going to learn a sequence of decision stumps. Recall that a decision stump is just a single split. And since it's in one dimension, it is a single split on this one dimension. So here's our training data. The x is a single real value number, and the y is a real value number. If you look carefully, you notice that this is y equals x squared. So we're going to learn a single split that minimizes the squared error of this training set. And it's going to be this split. So we're going to split right here. We're going to predict the average over here in this leaf node, and the average over here in this leaf node. And that's the single split that minimizes the training error of the squared error of the training set. Excuse me. And now we're going to compute the residual. So that's y sub 2 here. So this new column here is what's called the residual. And the residual is simply what's remaining from the ground truth after you subtract off the current prediction. So the current prediction for the top 5 data points are 6. And then the current prediction for the bottom 2 are 30.5. And we're going to subtract that from the ground truth label, which is the original y column here. And you get this y sub 2 column, the residual. I'm going to train a second regressor whose training data, whose ground truth labels are y2. So I'm going to train, so the x's stay the same, but y2 is now changed. The label I'm trying to fit to when I train h sub 2 is going to be these labels, right? And so I'm going to find a single split that minimizes squared loss when these are the labels. And I get this split, and these are the predictions of the 2 leaf nodes. And now my aggregate predictor, I call this h1 colon 2, is the sum of the 2 predictors. So I have an input x. I run the x through both h1 and h2. I get the output of h1 and h2, and I add those together, and that's the number I get here in this column. Again, I compute the residual, and I create a new training set with the same x's. The x's are the same, but the y's, the labels are changed to this now. And I do this process, train in h3. My new aggregate predictor is h1 plus h2 plus h3. I keep doing this process until some termination condition is met. So that's the general gist of boosting. We're going to go through a few different versions of it, but that's the general gist of boosting. Question, yes?
I was wondering, would it not make sense to sort the y2 values before running 2 with x on it? Because then you would...
It's sorted by x.
It's sorted by x.
It's always, so in training decision trees, you're always spatially placing data according to the input features, which is x.
Because isn't the input to h2 the y2 value?
The input to h2 is x. The training of h2, the prediction of h2 is the y values. Are the y values. So for decision tree training, and in general for machine learning, you want to sort the data. If you want to visualize the data sets, they should be spatially organized according to their x values.
Okay, so y2 are the labels.
Yes, that's right. Yeah. I'm modifying. This process is actually modifying the labels of the data points. The data points don't change. So this is one-dimensional regression. So the data points are x equals 0. Where's my cursor? X equals 0, x equals 1, x equals 2, so on and so forth. Those are my data points. They don't change. This is a 1D problem. In fact, it's probably easier to if I plot it, it's probably easier to understand. So, so this is just a plot, a cartoon visualization of what happened in the previous slide. In the top left corner, you have the actual training data, the original training data, which is just y equals x squared. So the x-axis is the one-dimensional feature, and the y-axis is the target label. I train a decision stump, and by the way, t here indexes the iteration of learning. So I train a decision stump, which is just a single split of the data, and I have a single average prediction of the left nodes and a single average prediction of the right leaf node, and that's what this looks like. So this is what the predictor looks like on the input training data. And then the average predictor, the aggregate predictor, the ensemble predictor is the same because it's only a single predictor right now. What you do now is you compute the residual. So this is the residual, which is just this guy minus this guy, or sorry, minus this guy, and these two are the same in the first case. And so the data points in terms of their feature values are still the same. Their labels are now different. Sorry, the scale is a little bit off. So this is only scale from 0. This is scale up to 10. This is scale up to 40. Now I train a new predictor, who's again the x values, the input feature values of the training that are exactly the same. They're unchanged, but their labels have changed. Predict a different split of the training data, and these are the new predictors of this decision stump. The aggregate predictor is now the sum of H1 plus H2. That's this guy right here. And now I again compute the residual of the original training data y1 with this aggregate predictor down here, H1:2, and I get this as my residual. Again, the input x features are unchanged. They're exactly the same, only the labels on the data points have changed. And this process continues. Any questions? Yes?
Are you assuming that so you assume that you train left like H1 to HT or whatever. So there's no, like, if you had like more data or something, or you're trying to go through, like run this in real time, right, where you like one data point after another.
Right, so the question is there a stochastic version of this learning algorithm? Is that what you're asking?
Yeah.
Is there a stochastic version of this learning algorithm? Yes, there is. It doesn't work. So again, this is a meta approach, right? To the extent that there's a stochastic version of decision tree training, there's a stochastic version of this algorithm. I can imagine training a sequence of linear models, right, using stochastic gradient descent, and then there would be a stochastic version of this algorithm. So the first answer is, since this is a meta algorithm, if there's a stochastic learning algorithm for your base learner, then yes. Yeah. There are, of course, cases where that abstraction breaks down. You can't do that abstractive reasoning. But in general, that's the answer. OK, so here's a concrete algorithm. It's called gradient boosting. It's almost exactly what I just showed you. And if you're interested in gradient boosting in general, it's a very old algorithm now, and you can this reference down here in the bottom left is a pretty good reference that explains gradient boosting. So it's almost exactly as I described. First you train a single weak model. Here it's a 2-layer decision tree, which is still pretty weak in this example. You create a training set, which is where's my mouse? Here we go. You create a training set. Again, the input features stay exactly the same, and I just manipulate the labels so that it looks like the labels are now the residual. I add it, so on and so forth. And so this method is called gradient boosting. This is the simplest version. It's basically the exact same thing that you guys saw before. And there are slightly more complicated versions that have been proposed that look a little bit different. But that's the basic idea. So let's try to think about what gradient boosting is actually doing. So And to explain what it's doing, I want to talk about axis-aligned gradient descent. So let's go back to a linear model. So h of x equals y w transpose x, excuse me. So no bias here, just for simplicity. And we're going to look at squared loss. So our loss function is squared loss. And we're going to do gradient descent, but we're only allowed to do axis-aligned updates. So what that means is we're only allowed to update one dimension of the features at a time. Or excuse me, we're only allowed to update one parameter of w at a time. And so what does that look like? Well, that looks like, the gradient has to be projected onto one of the basis vector, one of the axis-aligned basis vectors. And so if we're doing gradient descent, if we want to take the direction of biggest descent or biggest progress, which basis vector do we choose? Well, we choose the basis vector that has the largest projection from the gradient. What does that mean pictorially? In 2D, that means, here's the gradient, and let's say the horizontal direction has larger magnitude than the vertical direction. Sorry, it's I realized that the projection aspect ratio is a little bit squished. I wasn't able to fix it prior to the start of lecture. It's more obvious in the bottom left. So here, if you look at this gradient, which is the yellow vector, the vertical component is much bigger than the horizontal component. So if we can only make an axis-aligned update, so only update one element of the vector at a time, we would choose the vertical component. Okay, so you could think of a linear model as a model of one coefficient per feature. You can think of ensemble methods as one coefficient per model, which means that I have a set of models, I have a set of functions, and I'm learning an additive or linear combination of these functions. For a linear model, if you live in a d-dimensional space, you can think of there as being d functions. Each function makes a prediction along only one feature, and then I just do some weighted averaging of those functions. But in general, ensemble methods are just coefficients over more general notions of these functions. So a function space, you can think of a function space as one whose axes are the set of all shallow decision trees. So I'm going to define a function space, and every axis, and this is an infinite dimensional function space. Every dimension corresponds to a shallow decision tree. And the coefficients are now either 1 or 0. So I put a 1 if it's in my ensemble and 0 if it's not in my ensemble. In general, it could be more other values beyond other than 1 or 0, but in this example, let's say 1 or 0. So these are mathematically equivalent representations of what's happening. So there's some properties of function spaces. They're in many ways a generalization of a vector space. They're closed under addition, closed under scalar multiplication, and now we can think about things that look like gradient descent in function space. And to go to your question, you asked the question whether the combination of two decision trees is a decision tree. The answer is usually not. Here, all I'm saying is that the axes are decision trees. The function is just a function that lives in this function space whose axes are decision trees. So it's still consistent with the answer I gave before. It's a subtle point. Mm-hmm. Okay, so every axis in this function space corresponds to a weak model. So typically, as a thought experiment, there's an infinite dimension. It's an infinite dimensional space. Complex models correspond to linear combinations of weak models. And this is equivalent to a point in this function space, where the points are defined by the coefficients in this eta vector. So now, let's go back to axis-aligned gradient descent, where we compute a gradient, but we're only allowed to make an update along one axis of the space of the functions that I'm learning over. So I project onto the axis of greatest progress. What that look like if I implement it in function space? Well, I need to choose the shallow decision tree that reduces the squared error as much as possible. And that's actually mathematically equivalent to training a decision tree, finding a decision tree that minimizes the prediction error with the residual. If you actually work out the math, that actually is what's happening here. In practice, of course, all this mathematical explanation is not entirely relevant in your day-to-day life. I just wanted to sort of explain how these concepts are all tied together. And if you're interested in research, of course, these types of mathematical concepts may become more relevant depending on your research interests. Yeah, my lab actually does a lot of work in functional gradient descent. Any questions? Yes?
Sorry, I'm just having some trouble understanding like what gradient with respect to like a function means. Like,
Yeah. So I'm going to take the gradient. So a gradient is in finite dimensional space. A gradient is a vector of directional derivatives, right? So and so in infinite dimensional space, even though I can't explicitly write it down, any particular component of it is a directional derivative. Right, so how do I minimize squared loss as a function if I were to increase my coefficient? So this one I'm setting the step size to be 1, but in general, the steps you could think of this eta as corresponding to like a step size in learning. So that's like saying I'm going to add a coefficient of magnitude eta to this axis. And so in finite dimensional space, just repeating myself, just to give you a chance to digest what I'm saying. In finite dimensional space, a gradient is just a vector of directional derivatives, and then we take a step size, so we add a small component of that to our model. In function space, of course, the way you think about it is it's this infinite dimensional space. And so you can't write it down explicitly, but you can still think about conceptually what each entry looks like. And every entry is a directional derivative as a function of if I were to increase my ensemble classifier with more weight from this decision tree, how does the squared loss change? And I'm going to choose to add weight to the decision tree that has the biggest change in squared loss. So that's the projection operator, right? Just like if I only make a gradient update along a single dimension in a finite dimensional case, I just look at the directional derivatives and pick the one with the highest magnitude, right? That's a projection operator. Here, the projection operator is I have to look at it over an infinite dimensional space. That's equivalent in the squared loss case because of how the gradient of squared loss works, right? This is if you actually look at this, like, it looks like the gradient of squared loss, and because of how the gradient of squared loss works, it's equivalent to just computing the residual, what's left over and not being predicted, finding the decision tree that is closest to that residual, and that is equal to implementing this projection operator in this infinite dimensional function space. Yes?
So when I define a loss function over a function space, is it still like a scalar field, or like what is it now?
You may know more math than I do in this regard. I'm actually unable to interpret your question.
But if I take the gradient with respect to the function, I still induce a vector field over the function space?
I think so, yeah.
Okay.
It's just infinite dimensional.
Mm-hmm.
Yeah. Yeah, it's just infinite dimensional. Yes, question?
What's the termination condition for this?
Right, so what's the termination condition of this? Let me see if I cover it later. They're what you might expect. You have a held out validation set, and you see if test error, validation error keeps going down or not. And it's fairly standard compared to everything we've discussed so far. Yeah. Right. So you can do a reduction to vector space where there's a finite dimension, and so you can show that linear models doing axis-aligned gradient descent in a linear models is a special case of everything I described. Yes.
Sorry, would it be wrong to say in this case that like decision stubs form a basis for this function space?
That's right. That's right. It's just an infinite number of them. Yeah. Okay, so the full version of gradient boosting is slightly different in that there's this thing here, this eta term, which is usually much less than 1. You can think of it as a learning rate. And I'm not going to go over the details of that. You can see this paper for how to set this learning rate properly. But this is an algorithm, gradient boosting. These days, it's actually still surprisingly popular. There's a packet or newer versions of this method are still quite popular. There's a software package called XGBoost. Anyone hear of XGBoost? Okay, so XGBoost is a boosting algorithm, and it boosts decision trees. So this is a super simplified version of that is part of XGBoost. Yes?
So you can use that with any type of algorithm. That's the use with decision trees, right?
So the question is, why are we talking about decision trees? And we could use this with any algorithm. And the answer is yes, we can.
It's much better with decision trees, right?
So decision trees have some nice properties. So the question of why everyone talks about these methods with decision trees has two facets to it that I don't know if everyone's interested. I guess I'll just talk about it. So one is historical. So at the time where these methods were being invented, decision trees were the most interesting nonlinear classifier we have. Deep learning didn't work at that time. So one reason is just historical. Deep learning only started working around 2011, 2012, and these methods were invented in the 80s and 90s. And at that point, decision trees were already working. So that's one reason, so historical. The other reason is a little bit more practical in that there are many data sets where training decision trees is super fast, but training deep neural nets are much, much slower by comparison. You'll need a GPU and stuff like that. So if you want a quick method that gives you almost the same accuracy as a giant deep neural net, but trains like a 1/1000th of the time, then you want to do something like this.
So is it being used with deep neural nets or models?
Right. So yes, people do ensembles with deep neural nets. In fact, one of the winning Kaggle submissions from a few years ago was an ensemble of deep neural nets. Was a layer of ensembles. It was an ensemble of deep neural nets and a random forest ensemble together. So if eking out that final 0.1% accuracy is worth millions of dollars, then you know what to do. Yeah. Yes, question.
So like if you're actually trying to put something into production, is it practical to have like many ensembles?
Right. Okay. So the question now is, okay. So what about computational cost, without memory cost, cache, all this stuff that are the realities of actually serving one of these models on, let's say, a web server that has billions of hits a day. So you're absolutely right. There is a prediction. It's actually not just computational cost. It's also latency, right? So these models, these bigger models, they might take longer to run. And if you're doing, let's say, high frequency trading, and you need your algorithm to run in like nanoseconds or whatever it is they do, then these big models, they can't do that necessarily, especially if it's like a 100-layer neural net. You're sequentially blocked by every layer. And so I don't have a good answer to that question, but in general, people have these profiles of like various cost metrics versus how much the accuracy decays, and then you have to make a business decision of what is good for the business. Right. So you may not want to put this in like a low resource like your phone or a small drone or a medical device. So Azita Amami, who's a professor in electrical engineering, part of her research studies these medical devices that get implanted in the human body. And as you can imagine, these devices have very low memory and power capacity. And so, even if you have a gigantic ensemble of deep neural nets that get 99% accuracy versus a smaller set of models that have 98.9% accuracy, you may choose the slightly less accurate model. Okay, so just to recap, boosting as a generic concept is looking at an ensemble of many weak classifiers with the goal of reducing the bias of these low variance models. And one way to think about how you derive the algorithm is through axis-aligned gradient descent in function space, where the axes of this function space are the set of weak models. Any questions so far? Okay, so on to the main topic of today, which is AdaBoost. This is one of the most classical algorithms, one of the most famous algorithms in machine learning over the last 20, 25 years. So, and the reason why it's such a classical algorithm was, at the time, boosting was, you can do it for regression. But coming up with a principled algorithm for boosting for classification remained somewhat elusive. And so the AdaBoost algorithm was one that sort of definitively answered that question. And so that's one of the reasons why it's such a famous algorithm. It's not as popular these days as it used to be, simply because we have better and more practical methods. But as a thought experiment for understanding how we design new learning methods, it's a very relevant one for teaching purposes. So AdaBoost stands for adaptive boosting. So AdaBoost is also an instance of functional gradient descent. Since we're doing classification, one thing to keep in mind is that the aggregate model, you take the sign of the base model. So the base models are just scoring models, and then we take a linear combination of them, and then we take the sign of that for our final classification, because we're doing classification now. So that's one small change between this and the previous boosting aggregation methods that we saw before. Oh yeah, so I should also mention the base models are also classifiers. I should have mentioned. So they all either predict 1 or -1. So we're using -1 here because it makes the math more convenient. If you want to do 0 or 1, everything still works out, but the math gets much uglier. Okay, so before we talk about the learning algorithm, let's just go through some examples to get some intuition. So I'm going to use f here, and for this lecture, I'm going to use f to denote the raw scoring function. So each h is a base decision tree classifier. Let's say a shallow decision tree that predicts +1 or -1, and then I'm learning a linear combination of them. And then the aggregate one just takes the sign of f of x. Okay. So let's say I'm looking at 4 data points. Their feature values don't matter, but I'm going to look at each of the 4 base classifiers in this example predict on those data points. So on the first example, we get +1, +1, +1, -1. The second example, we get +1, +1, +1, +1. The third example, -1, +1, -1, -1, and so on and so forth. And these are our weights, right? So this is a linear model in this space where the values of these where the input features are the outputs of my basis functions. And so the final predictor looks like this, and the raw score looks like this, with these coefficients, 0.1, 1.5, 0.4, and 1.1. Okay. So, one thing that's kind of interesting about boosting methods is that, like bagging, they create new data sets. Unlike bagging, they create new data sets by manipulating something about the data. For example, in the previous example, we manipulated the label to be the residual. So in bagging, we're creating the data sets by doing this resampling process, but each data point was uncorrupted. It's just the presence or absence or the multiplicity of that data point in the new sample data set. In boosting, we are always manipulating the data. So this is algorithmically equivalent to training another weak model on a modified version of the training set. Okay, so how do we do this for a classification problem? So it's, for regression, because of the simplicity of squared loss, it's easy to show that the modification you should make, it's easy to show, is you should just change the label to be the residual. But what about for classification? So was that a question? Okay. So for classification, for AdaBoost, algorithmically, it's going to look like reweighting the training data. So we'll define a weighting. I'll call the weighting D over the training set. The weighting sums to 1. And so examples include uniform. So if I have a data set of size 3, I could do a uniform weighting. I could completely discount or ignore one of the training data points and uniformly weight the rest, or just whatever I want. These weights are non-negative weights that sum to 1. And now, given these weights, I want to train a weighted loss function. So this is the loss function I'm going to use. So the only difference between this and a normal loss function is that the weights are not uniform. In a normal loss function, you add up all the data points and you treat them equally importantly. Here, I treat them with unequal importance depending on their weight. And so just a side comment about training with these weighted loss functions. So in general, AdaBoost assumes that your base learning algorithm is able to learn a model from a weighted loss function. You might wonder how that works for decision tree training. And you can just do it by simply a weighted version of your information gain or splitting criteria. So here's Bernoulli variance, and you can just simply do a weighted version of that by when you compute the fraction of positives and negatives, you do a weighted fraction rather than an unweighted fraction. So it's a very simple modification to decision tree training can get you, it makes it able to train these weighted importance loss functions. Yes?
And do they have to be non-negative?
Yes, it turns out that this weight ends up corresponding to a distribution. So before, it was a uniform distribution over the training data. And it'll end up having an interpretation of a distribution. Okay, so here's the AdaBoost outline. So initially, the weighting is uniform, so just a normal learning problem. We train a weak classifier. We reweight the data, so it's the same. So the x, y, the labels, the input features and the labels are the same, but I'm going to explicitly and purposely reweight the data in some way. We train a new weak classifier, add that to my ensemble. Based off the predictions of my ensemble, reweight the data again purposefully, and keep doing this. And then the stopping condition is, let's say, when the validation performance stops going up. Okay. So now let's talk about the secret sauce here is how do you reweight the data. So we've boiled everything down to how do you reweight the data as a function of how well the current aggregate classifier is doing. So let's look at this example. Here are the labels: +1, +1, +1, -1. That's the ground truth labels. these are the raw score, and then this is the sign of the raw score, okay, of the aggregate, of the current aggregate model. Okay, so let's look at the second row and the fourth row. In the second row, the ground truth label is +1, and the raw score is 3.1. Very, very, very far from 0. Very far from the decision boundary. In the fourth row, the ground truth label is -1, and the raw score is -2.4. Again, very, very far from the decision boundary. If I were to add another model to this aggregate and that model perturbed that score, it's most likely still going to be predicted accurately. It's not going to push the raw score across the decision boundary. Okay, let's look at the first row. Somewhat close to the decision boundary. So you can imagine a case where if you add another model to your aggregate model, this guy might be misclassified or be dangerously close to being misclassified. Okay, the third row, it actually violates the decision boundary. And even if the raw score was a little bit different, or let's say the raw score was 0.1 instead of -0.1, it would still be a bad example in the sense that if we add another predictor to our aggregate, it could very easily cause this thing to go bad. So as a thought experiment, so we know that how the algorithm works at a high level is we have the current aggregate predictor. Based on the performance of the current aggregate predictor, like in these 4 examples, we reweight the training data and we train a new classifier on a reweighted version of the training data, and we add that to the aggregate predictor. So here's a thought experiment. What happens if we train a new H sub 5 and we just do a worst case analysis and it mispredicts on everything in terms of these first 4? Okay, so let's suppose that the coefficient, I'm just simplifying the analysis just because it's a thought experiment. Let's suppose that the coefficient is 0.5. So the coefficient of the 5th predictor is 0.5. So then this is the new updated raw score. If this predictor is, for whatever reason, mispredicted on everything in the first 4 examples, then what is the impact? What is the impact of adding this model to our original, our current aggregate predictor? Well, for the second and fourth row, because the current aggregate predictor was already so far from the decision boundary, I don't care. For the first row, because it was already kind of close to the decision boundary and we're making it closer, it's kind of bad. It's getting dangerous. And for the third row, it's really bad. We were taking a prediction that was somewhat close to the decision boundary and pushing it much further from the decision boundary in the wrong direction. Okay, so what does that mean? That means if we really care that for the next model that we add to this aggregate predictor, it gets the third data point right. It probably should get the first data point right, and I could put 0 weight on. I could care 0 about whether it gets the second and fourth data point right or not, because it doesn't change my aggregate at all. In other words, the desired weight, if I were to reweight the training data to train a new aggregate predictor, to train a new base predictor to add to my aggregate, I should put a high weight on the third data point, a medium weight on the first data point, and a low weight on the second and fourth data point. Okay, and that is the AdaBoost algorithm, and we can formalize it with the concrete weighting scheme. We train a classifier on the current weighting scheme. It's initialized as uniform. We have a step size, so we figure out a coefficient. So we compute an error, so how well it performed. And then we have a step size that determines how much weight we add to the aggregate predictor. And then we update our weighting. And then finally, we return this aggregate predictor. And so this formula looks kind of complicated, and you will become very familiar with it at the end of homework 3. Let's go through an example to actually walk through some intuition about what this formula is doing. So keep in mind that each of the base classifiers, they predict +1 or -1 for each input example for the definition of add a boost. And so this A is the coefficient. The Z is a normalization factor so that the new weighting sums to 1. So we multiply the previous weight by this exponential term, and then we make sure the whole thing normalizes so that the distribution sums to 1. So let's just go through a simple example. So we have this first 4 data points, and there's many more data points that I'm not going to look at. And let's say there's 100 data points. So the weight, or rounds to about 100. So the weight is about 0.01 initially, and we get some of them right, some of them wrong. So this is the current model. So it gets the first one right, it gets the second one wrong, it gets the third one wrong, and gets the fourth one right. Okay, so then let's look at what this formula does. So this formula says, y is the ground truth label. So in this case, it's 1. You multiply it by h, which is 1. And then you also multiply it by the coefficient, in this case 0.2. And then we multiply by e to the minus all of that, which means that if this number is a large positive number, then the weight goes down. If this number is a large negative number, the weight goes up. And it's positive if the prediction h of h matches the label. That's when it's positive. And it's negative when the prediction of h does not match the label. Their signs don't match. So if I predict it correctly, then the weight goes up by a multiplicative factor. Or sorry, if I predict it correctly, the weight goes down by a multiplicative factor. If they're mispredicted, the weight goes up by a multiplicative factor. And that's what you see here. And then I renormalize so it sums to 1. So that's what you see here. I train a new model, h sub 2, on this training set, but now the weight is not uniform. The weight is this guy. So I care more about x2 and x3, and I care less about x1 and x4. And then again, I look at okay, this guy it gets predicted accurately, so the signs match. So e to the minus that it means that I multiply this by something less than 1. So I go from 0.8 to 0.7, 0.008 to 0.007. This guy I get right, so this weight goes down as well. This guy I get wrong again, so the weight goes up, and so on and so forth. That's basically how it works. These numbers will not completely compute exactly. I just made these numbers up for visualization purposes. But that's the basic idea. Yes, question?
Notice that the error went up after you added a second.
Correct. So the error is on. So first of all, the error is on this rating.
Okay.
Yeah. So the only assumption is the error is a little bit less than 50%. Otherwise, there are no assumptions or no expectations of what the error might be.
And that's because you're weighting the misclassified points higher, so the error is going to be shifted up.
Well, the error gets shifted. Like what data points matter more gets shifted. Yeah. And so this process continues. So one thing that's kind of weird is, if the error is actually exactly, so this is the formula for choosing the step size, by the way. If the error is exactly 0.5, then this formula doesn't actually compile into something that you can actually implement. So there is a critical assumption that the error is, not 50-50. You're doing better than random guessing. Okay, so let's talk about the interpretation of this as a form of functional gradient descent. So we're going to define a new loss function that we haven't seen before. Hooray. This loss function is called exponential loss. So exponential loss is defined by the formula up here, and it's designed for classification. So it basically says the loss you get is equal to minus the ground truth label times the raw score. So if the raw score and the label agree in sign, then you get e to the minus some number that's a very big number, which means the exponential loss is close to 0. If the raw score and the sign of y disagree, and the raw score is very big in magnitude, then you get something like e to the big number, so then it grows very quickly. So this is a loss function. It's a surrogate for 0-1 loss. It's a smooth surrogate for 0-1 loss. And you can prove through some algebraic manipulations that the procedure of AdaBoost is actually doing functional gradient descent for minimizing 0-1 loss. Sorry, minimizing exponential loss. So some interesting properties of 0-1 loss is to help exponential loss is to help you get started. So this is the form of the exponential loss. This f of x is the sum of this weighted sum of the base functions that you've collected in your ensemble. Because of how exponentiation works, this is equal to the product of the exponentiation of the individual components. And now this looks a lot like the distribution update rule. Right? This looks a lot like the distribution update rule. Right? And so in some sense, the exponential loss operates in the exponent space. So as I'm aggregating these models and adding them to my aggregate model, I'm basically multiplying some term to my current exponential loss. Because without the last aggregate model, my exponential loss is just all these things. It's just all these things without the last term multiplied to it. When I train a new model and I add it to my aggregate predictor, how does the exponential loss change? Well, I just multiply the individual exponential loss to the total exponential loss, and that's the exponential loss of the aggregate model because of the equivalence of multiplication versus adding in the exponent. Again, this is just what I said. So the reweighting scheme in AdaBoost can be derived via residual exponential loss. And it's a homework assignment. Any questions? Yes?
Is there some relationship between AdaBoost and some maximum entropy interpretation, like statistical mechanics or something like that?
Not that I'm aware of. Okay, yeah, that's what I just said. Yeah, these are the steps to prove it, but the homework assignment walks you through it. So it's to help you understand how to do these algebraic manipulations to give these multiple interpretations of what an algorithm is doing. One of the nice things about these different, I should just mention this as a high-level thing. One of the reasons why we do this is that if you want to actually understand the behavior of a learning algorithm, oftentimes it's hard to understand it from one particular viewpoint or one particular interpretation. But then you shift your interpretation of what the algorithm is doing. And again, we can establish that they're all mathematically equivalent. But it just turns out that for a particular problem, once you shift your perspective, it becomes much easier to actually analyze the behavior of this algorithm. Like, oh, is it going to converge? How quickly does it converge? And all these questions you can analyze if you just frame the problem the right way. And that's part of the process of trying to find all these equivalences and trying to understand that they're all mathematically equivalent, but some of them are much more mathematically convenient, like the geometric versus optimization perspective as support vector machines. Like reasoning about, I could write down the optimization problem of a support vector machine with hinge loss, and I can say the solution only changes if one of the support vectors in the data set gets removed or added. Otherwise, the solution doesn't change. I could also show you geometrically what the support vector machine is doing and it's just blindingly obvious that that happens. So when you try to understand different properties of these learning algorithms, it's important to be able to simultaneously understand that there are many valid interpretations or viewpoints of what they're doing. And so this is a way to relate a seemingly where did they came up with this algorithm kind of thing to understanding, oh, they're just doing residual exponential loss in functional gradient space. Okay, that's okay. Anyways, okay. So just to recap, AdaBoost is gradient descent, axis-aligned gradient descent in function space over a space of weak classifiers. The final model is a linear combination of these weak classifiers, and the coefficients A correspond to a point in this function space. And procedurally, how it works, when you implement it, is it iteratively creates a new training set by reweighting the data points in the current training set. And you can show that this is equivalent via derivation of minimizing residual exponential loss. Any questions? I also understand that perhaps this type of math is a bit abstract. In fact, this is probably the most abstract part of this class. But if you're interested in machine learning research, this is definitely an area of, ongoing activity that is very near and dear to my heart, actually. Okay, the last thing I want to talk about today is ensemble selection. So just to recall, we have this bias variance decomposition, and we spent all this time thinking through this thing very carefully. And I'm sort of going to spend the last 10 minutes bashing what we've just spent the last several lectures talking about. Right. So, a lot of smart people over the last 25, 30 years, they've been thinking very carefully about this bias variance decomposition, and trying to come up with methods. Some of them are now very iconic, like bagging and boosting, where bagging, tries to average a bunch of high variance, low bias models, which reduces variance, and indirectly deals with bias via starting off with low bias base models. Boosting says, okay, well, let's carefully combine simple models in a way that reduces bias, and by design or by construction, these models have low variance to start with because the base models all have low variance, excuse me. Can we get the best of both worlds? And so one insight is that, well, we can just use a validation set. So here's an idea. We can evaluate the error of our model by looking at its error on the validation set. The validation set is an estimate of the error on the test set. In the end, we're trying to minimize the sum of bias plus variance, which is the test error. We could, rather than trying to carefully try to tease apart where the error is coming from, let's just measure the error on the validation set and forget where it comes from. And so that is ensemble selection. So we have a training set. We split it into training and validation. We train a bunch of models on the training set. And so I'm arbitrarily saying 2,000 here. And then we maintain an ensemble model as a combination of the models we trained up here. And then we add a model that maximizes performance on the validation set. So every time we consider adding a model, we ask, does adding this model to our current ensemble improve the performance on the validation set? Yes or no? If yes, we pick the one that has the maximum improvement, and that's it. Repeat. Okay, so importantly, the models are trained on S prime, but the ensemble is built on V prime. So we're controlling for overfitting this way. Okay, so bagging says we're going to reduce variance on low bias models. Haha, we're so clever. Boosting says, oh no, we're going to reduce bias on high variance models. We're even more clever. And ensemble selection says, well, who cares how clever you are? If we could just directly get a measure of test error, then we can just optimize for that. So, sounds too good to be true, right? And it is, sometimes. So what's the catch? Well, it relies very heavily on a validation set, right? So much more heavily than bagging and boosting. Boosting only uses a validation set for early stopping. This uses the validation set to build the ensemble. So the validation set needs to be sufficiently large, and it also implies much smaller training sets than bagging or boosting uses. So your base models are just weaker, systematically weaker than in bagging and boosting, because you're partitioning your training set into smaller pieces. So that's the catch, and because of that, sometimes it doesn't work that well. But if you're mindful that this is the catch, and you think again, there's a little bit of art here, but you think that it's still okay, then this can work very well in practice. So there's been a number of experiments done on these types of methods, and ensemble selection often can perform extremely well, winning lots of competitions in terms of things that are like the Kaggle competitions, like the KDD Cup. There are many papers written about ensemble methods. And these days, I guess I don't have a full updated list, but these days there are many ways to do ensemble of deep neural nets for those who want to eke out that last bit of performance. So there's even more than what's on here, but if you're interested, so here's a reading list. Again, the slides are on the course website. Any questions? Okay, next two lectures are on deep learning. Recitation on a deep learning package called PyTorch is this Thursday.